Good morning, grade 10s. Um, this is me recording the first lesson in the chemistry unit, and I'm also trying out a new tool, Flashback Express, and so we'll see how that goes. The title of the unit is Chemical Reactions, and so it will be a continuation of the chemistry unit in grade 9 that you began last year. So the main difference between the chemistry unit in grade 9 and the chemistry unit in grade 10 is that in grade 9 you were just being introduced a little bit further into the nature of chemistry in terms of substances. What are what is matter? What is matter made of? How does it behave? Uh, what are atoms made of? What do they look like? What's the difference between a pure substance and, let's say, a mixture? We'll get to that. We'll review that in a few minutes. In grade 10 chemistry, we want to go further. We want to look at how chemicals interact with each other, how they behave when they react. So what is a chemical reaction? And how can we predict what's going to happen? Why do some chemicals react and some chemicals don't react? So again, it's a follow-up to grade 9, but we're going to go further. So you can see the fundamentals of chemistry is understanding what matter is. And we see here the two sayings. What in the world doesn't matter? What in the world isn't matter? Matter is everywhere, and almost everything is made of matter. But if you review what you learned in grade 9, you see that matter is really important. Now, this is what you learned in grade 9. The, do you remember learning this? That's maybe another question. But let's go through this as a review. And you did, hopefully, if you're following the instructions in the lesson plan, you've done the diagnostic quiz. You've tried to fill out the grade 9 review worksheet with maybe lots of success, maybe limited success. Do you remember some of these terms? Well, let's go through. Let's review some of the terms. So first of all, the word matter itself. What does matter mean? Matter is anything that has mass and takes up space. And based on what you learned last year, you also know matter is made of atoms and molecules, which are groups of atoms which stick together in bonds. And we'll review that later. But anything that weighs something or anything that takes up space is matter. And it can be solid objects, like these headphones I'm wearing. Our bodies are mostly solid. The wall behind me, the curtains in my office here. Matter can be liquid, so the coffee in my coffee cup here. Obviously water. Matter can also be gas, so the air in this room floating around, of course, can't see it because the naked eye cannot visualize individual atoms and molecules floating around if they're not condensed together. But there are oxygen particles, there are carbon dioxide particles, there are nitrogen gas particles, and there are others. There's even water vapor floating around in this room. You can't see it, but those are particles. That's matter. But we can divide matter up into two categories here. We can say that there are substances, matter, which is uniform. That is, the substance is made of the same particles throughout. The substance is made of the same particles, or at least it appears uniform. It looks like it's made of the same substances throughout. And so if that's true, if we say if it is uniform throughout, I look at it and I say, okay, it looks like it's made of the same thing, then we're going to call it homogeneous. Now, if it doesn't look like it's made of the same substance throughout, it's very obvious that it's not, then we can easily call it a heterogeneous mixture. So if you pick up a handful of dirt, for example, and you hold it in your hand, you say, okay, clearly I can see different grains, different particles, sand particles, clay particles, maybe some bits of grass in there. That's very obviously a heterogeneous mixture. If I hold, a trail mix in my hands, and I say, okay, I see raisins, I see nuts, I see M&Ms or whatever, Smarties, I say, okay, that is clearly a heterogeneous mixture. There's lots of different things there mixed together. Sometimes it's not so easy though. If I look at you won't be able to see this very well, but maybe if you can look into my coffee cup here, you can say, okay, it's it looks like it's one substance, but actually I can kind of see little bits of cream. I'm getting near the bottom of my cup now. So I see little bits of cream floating around, and it's not quite the same. Can you see this? It's not quite the same as the rest. So then I would say, okay, this is probably a heterogeneous mixture as well, this coffee in the cup. But if you look at a lot of liquids, if you just look at a glass with water in it, and you look at that water, you say, okay, I'm not 100% certain if that is pure water or if there are things maybe dissolved in that water. Maybe it's salt in there, maybe there's other substances dissolved and I just can't see them. Um, but it looks like one substance, then that's homogeneous. So once you've decided whether it's heterogeneous, it's clearly a mixture of different things, or I can't tell, it looks like it's one thing, then you move on to the next branching category here. Does it have a variable composition? And what that means now is it actually, if I were to zoom into the individual atoms and molecules, would it be made of one type of particle, or would it be made of a mixture of particles? So if it's made of a mixture of particles, then we're going to say it's a homogeneous mixture, or we also call this a solution. So one of the questions on the quiz was a tricky question, the diagnostic, because it asked you about an alloy like white gold. My wife has her engagement ring and her wedding ring are white gold because she's allergic to regular gold, or it forms a bit of a rash on her skin, but white gold doesn't. And white gold is actually an alloy. It's a mixture of gold and some other metals. Now, because that is more than one particle, but it looks homogeneous, then we call it a solution. When we think of a solution, we usually think of a liquid. We think of, let's say, salt being dissolved in water or sugar being dissolved in water. And that is a solution too. That's a liquid solution. But you can also have gaseous solutions and you can have solid solutions. So the air in this room around me is a gaseous solution. I know that there are many different molecules floating around in the air. There's oxygen, there's carbon dioxide, there's nitrogen, and there's probably lots of others that I don't even know. But I can't tell. They all look the same. And so if it looks homogeneous, if it looks consistent, uniform, then we say it's a solution. Now, if it is in fact pure, it's only made of one type of particle, then we're going to call that a pure substance. Now, a pure substance doesn't necessarily mean it's made of just atoms. It might be made of just molecules as well. Remember, atoms can be individual atoms all by themselves, or they can be combined in molecules. So a glass of pure water, for example, is made of H2O molecules. But it is a pure substance because if it's pure water, it's 100% made of H2O molecules. If you have a chunk of pure gold sitting in front of you, then that would also be a pure substance, but that would be made of gold atoms. You know that they're atoms if they're on the periodic table, and we'll get to the periodic table later this week. Then the last category, is it actually made of pure atoms? Then we're going to call it an element, and again, the periodic table of the elements. So gold, carbon, hydrogen, oxygen, nitrogen, silver, aluminum. There's a whole bunch, right? There's over 100 elements on the periodic table. Or is it made of molecules? If it's made of molecules, then we're going to call it a compound. And again, there's different types of compounds, and we'll get to that later. So there's a bit of a grade 9 chemistry review. And actually, the rest of this lesson is also going to be somewhat review because we've seen this before. Section 5.1 in the textbook talks about chemical and physical properties and changes. And so we're going to go through these 4 concepts this morning and then give you a chance to work with that a little bit. So first of all, what is a physical property? A physical property is a description of any substance that does not involve forming a new substance. So when somebody asks you to describe something, what they're probably asking you is to tell them the physical properties of that substance. So if I ask you to describe the wall behind me, I would probably tell you what color it was. I would probably tell you whether it was painted or not painted. I would probably tell you whether it was plaster or drywall. I would be describing what I can see, what I can touch, what it feels like. So think of the senses. And so what are some examples of a physical property? A physical property could be the color of something, could be the texture, could be how dense it is. Think of the regular can of Coke versus the diet can of Coke question on the diagnostic quiz, right? How dense is it? Does it have a smell? Is it soluble? Can I dissolve it in another substance? Like salt, for example. Most salts can be dissolved in water. Sugars also can be dissolved in water. But starch, not very well. Um, Many substances, I could add it to water, I can mix it around, but it's not going to dissolve. It's not going to disappear. Does it have a taste? Also, physical properties include things like what is the melting point? At what point will a solid turn into a liquid? So for water, that's 0 degrees Celsius. And what about, you could also add boiling point to that. And even also physical and solid state. Physical state. Is it a solid? Is it a liquid? Is it a gas? That is also a description of its physical properties. Think also, physical properties can be classified as qualitative properties or quantitative properties. Qualitative properties are those that involve a description. Quantitative properties are those that involve a number. So think about the list that I have listed here. Which of these might be a quantitative property? That is, it actually involves a measurement, a number. So if you thought of the melting point as an example of a quantitative property, then you're right. Or if you thought of the density as a quantitative property, you're right, because the density is actually a number. What is the mass divided by the volume? That's the density. That's a quantitative property. The melting point, at exactly what temperature in degrees Celsius does this substance melt? But something like color or texture, these are not things you can put a number on. You need to describe it in words, so that's qualitative. So if those are physical properties, then what are chemical properties? Well, chemical properties are a description of what a substance does if it's changing into something new. A description of what a substance does if it's changing into something new. So this is harder to visualize, or harder to think about, because we're not used to doing chemical reactions that frequently. But think of frying an egg. Most of you have witnessed this, or even boiling an egg, but it's hard to see that because it's in the shell. But frying an egg, if I crack the egg onto a frying pan and I got the heat turned up, what happens to the egg white, especially as that egg cooks? Well, it's actually because of the heat, the proteins in the egg white are actually changing into something new. That's a chemical reaction that's occurring. And so a chemical property would be how do I describe what happens to an egg to an egg white when it cooks? What are some other examples? So, does a substance react with an acid or a base? That's a common chemical property. Is something flammable or not flammable? So I could say gasoline fumes are extremely flammable. I could say, a piece of paper under the right conditions is fairly flammable. But I could say, what would be a good example? This mug that my coffee is in, not very flammable, right? Maybe it will burn at some point with enough heat, intense heat, but it's not. I wouldn't say it's very flammable. Um, is something able to bleach things? So bleach, typical bleach or chlorine that we put in our pools is a bleaching substance. Hydrogen peroxide, if you add that to your hair, it'll cause it to become bleached. Those are substances that have bleaching ability, but they're actually reacting. They're changing when that happens. Is something corrosive? So most acids, for example, are corrosive. What that means is it'll eat through metal, or it'll break down metal. It'll also eat through your skin, so it's a good idea to not get those things on your skin. So chemical change is needing to happen when you're describing a chemical property. The particles are actually changing from particle A into particle B in order for this to happen. So that brings us to the idea of change. When something changes, is it a physical change or is it a chemical change? So these are related to the properties. A physical change is a change in the physical properties, a change in the appearance. You're not producing a new substance, you're just producing what it looks like or how it appears or how it's described. You're changing the properties without actually changing the substance. So a good example of this would be the property or the phase changes. So when a solid melts and forms a liquid, that's a physical change. When a solid dissolves in a liquid, again, think of salt crystals or sugar crystals dissolving in water or dissolving in your coffee or tea, that is dissolving. That's a physical change. The sugar or the salt is not disappearing. It's not changing into something else. It's disappearing to your eye, but it isn't actually gone. It's still there. When you taste the coffee with sugar dissolved in it, the sugar is still there. That's what makes it taste good. You just can't see it with the naked eye. It's dissolved. When a liquid evaporates to form a gas, that's evaporation, or sometimes we call that boiling, especially when we're talking about water. When a gas becomes a liquid, so if warm water becomes cold again, it'll liquefy again. That's condensation. And sometimes you can even have the liquid phase skipped altogether. You can go from gas to solid or from solid to gas. We call that sublimation. A good example of that is carbon dioxide, dry ice. When carbon dioxide is frozen, when carbon dioxide becomes very, very cold, it goes straight from gas to solid. And then when you release that into the atmosphere, it can go from solid back to gas. That's sublimation. You can also have physical change when you just physically change the shape or the texture of an object, like cutting a piece of paper in half or breaking something, right? If I smash this mug against the wall, it might break into multiple pieces. I'm not changing the ceramic that the mug is made out of. I'm not changing the substance. I'm just changing the appearance, the shape. That's a physical change. It should be noted that sometimes these are reversible and sometimes they're not. Okay, so if I rip a piece of paper, that's not reversible. I can't put that back together unless I have to use glue or tape. But often they are reversible. So think of melting versus freezing, or dissolving versus bringing something out of solution. Think of evaporating versus condensing. Those are reversible changes. So sometimes they are, sometimes they're not. So at this point, I'd like you to pause the video and try out these interactions. There's a self-quiz at this website, and these web links are also listed in the lesson plan as well. You can click on them. But this website here is a self-quiz asking you, testing your ability to identify physical changes of state. And this is a really cool simulation. I actually want to show this to you for a minute here. If I click on this second one, the PhET simulation, it'll take you to, oh, I already had it open, but it'll take you to this website here. And you can actually, there's two different simulations. You can try out the state simulation and the phase change simulation. So the state simulation looks like this. First thing I would do is change the temperature to degrees Celsius. So this is at a very, very cold temperature. So here we have a chunk of, it looks like neon. Let's do water. That's a little bit more relatable, but you can try the different ones. So here is a very cold chunk of water. So this would be what we would call a chunk of ice, but this is what the water molecules look like. And what this does is it allows us to do a phase change by heating up the water. You can see the temperature gauge going up. So what happens when I heat the water up? So now it's at 43 degrees Celsius. So now this chunk of ice is melting, basically. Okay, and if I just kind of hurry this along and I heat it up a little bit more, it's eventually going to turn into a liquid. So this chunk of ice is melting. It's becoming a liquid. And then as I begin, you can even see some water molecules are actually breaking off and becoming gaseous. And then if I keep heating this up into the hundreds degrees Celsius, now this ice, which is melting, is going to very quickly start boiling as well. See how the water molecules are speeding up. You could start on the other end as well. You could start with gaseous water. So click gas, and it starts you at 156 degrees Celsius. You can see what happens if I heat this up even further. Well, it's just going to speed the molecules up even more. So this is a gaseous water vapor floating around, but you could also cool it off very quickly. What's going to happen as you go below 100 degrees Celsius? The water is going to start to liquefy. Right, very quickly. Notice most of the water molecules have fallen down to the bottom of the container, and eventually, once you go below freezing, they're going to start actually freezing into a chunk of ice. So you can try that with different substances, different states. Now go over to the phase change. You can go home and click it, or you can go at the bottom there as well. But this is a really cool simulation too. The relationship between, again, I'm going to change this to degrees Celsius, but the relationship between temperature and pressure and a substance's phase change. So again, let's do water. Let's try oxygen for something different here. So what happens when I increase the pressure? I'm going to pump more oxygen molecules, like using this bicycle pump apparatus. I'm going to pump more oxygen molecules in here. And what's going to happen? I'm actually increasing the pressure. You can see that on the top on the pressure gauge. I'm also going to heat this up. See what that does. So we're now up to, try to get us up to room temperature, 20 degrees Celsius. See what that does. So here we are roughly at room temperature. So there we see the oxygen molecules are now floating around here. This kind of shows you at what point the substance will become solid, liquid, or gas. I could heat this up even more. I could also pump more oxygen in here, try and increase the pressure. But another thing I could do is actually lower the lid. Let's try and actually tighten this up. See what that does to the pressure. At what point is this container going to actually explode? Because it's just too much. So we're at 50 atmospheres, 75, 80, 90 atmospheres, 100 atmospheres. Notice how the temperature, as I'm increasing the pressure, I'm also increasing the temperature tremendously. And eventually, this is not going to be sustainable anymore. Boom, explodes. So you can try that out, that little demonstration out there. Okay, let's just go back to my lesson here and just finish this off. So the last one is chemical change. Chemical change is the change that a substance goes through to produce one or more new substances. So this is what we were going to call a chemical reaction. Now a chemical reaction is this is the foundation of, or this is the focal point of the unit. This is what we're going to be studying as we go through this chemistry unit in grade 10 science, is what are chemical reactions. Now the one thing we want to focus on just as in an introduction here today is what are some ways that we can tell that a chemical change is happening, that a chemical reaction is happening. Well, there are some clues that chemists have identified. We've known this for hundreds of years. What are some clues that a chemical change is happening? That a substance is actually, it's not just changing shape, it's not just changing phase, solid, liquid, or gas, but it's actually becoming something new. Well, one thing that often happens in a chemical reaction is you see a new color. So you add, chemical A to chemical B, and then a new color appears. That's a chemical change. Think of that egg in the frying pan. What happens to the egg white when it cooks? It was kind of a translucent clear color, and all of a sudden it becomes a very obvious white color. That's why it's called egg white. But that color change is indicative of a chemical reaction. Cooking and baking is a chemical reaction. Also, the production of heat or light. Think of anything where you have something burning, where you have a flame. Heat and light is being produced. Or sometimes it's being absorbed as well. So something getting really cold, heat is being absorbed. Another obvious clue that a chemical change is happening, a reaction is happening, is you get bubbles of gas. Now remember, it's important to distinguish this from turning something into a gas, like boiling water. When you boil water, you're just heating the water up and it's becoming gaseous water. That's not what we mean by bubbles of gas. What we mean is I add chemical A to chemical B, and all of a sudden you get bubbles formed, like when you add vinegar to baking soda and it starts bubbling. Carbon dioxide is being produced, something new, a new gas. This is a tough word, but try to remember it. A precipitate is formed. So when you add two liquids together and all of a sudden a solid appears in a liquid, a solid appears, that's called a precipitate. It precipitates out of the liquid. Um, in a lab, we would never ask you to taste or smell things because it could be dangerous to you, but a change in smell or taste is almost always a clue that a chemical change is happening, and also very difficult to reverse. Again, this is not a hard and fast rule, but it is a clue. Often they're difficult to reverse. None of these are conclusive evidence. These are only clues, but it does help you when you see these things happening. It helps you to distinguish, oh, maybe a chemical reaction is happening. So in connection with this, and to bring this lesson to a close, I'd like you to watch this YouTube video here. The link, again, I've also included the link in the lesson plan. And then once you've watched this YouTube video, I want you to practice some of these concepts that we've been introduced to today. And I'd like you to do that in the textbook, page 178, number 1 through 10, and also the worksheet that I've attached to the lesson plan, Physical versus Chemical Properties and Changes. Download that worksheet, complete it. The first page is the worksheet, the second page is the answer, and so you can do the work and then go to page 2 to check your answer right away. All right. Again, I'll be available during office hours from 10:45 to, from 9:20 to 10:45 today and all this week. And I would like this lesson, if possible, to be done by the end of Tuesday, if possible. All the best, and reach out if you need help.